I just cannot. Whatever, I don't care anymore. It's about 55% plasma. And it doesn't have cells. So we have something called colloids. Which is like albumin. And that accounts for about 60%, and that doesn't easily pass through the bloodstream, just because of like how big it is. Bloodstream, and then you have globulins underneath that, and these transport substances. And then antibodies are types of globulins, and then you have fibrinogen, which is a clotting factor. Yeah, if I'm right. We're fine. Okay, and then you have serum, which goes into the blood without any clotting factors. So, the gel electrophoresis of plasma. Okay, so albumin would rest around here. These are the cellular components that would make up blood. So red blood cells are around 45% of a person's, formed elements. So you have albumin, then you have alpha, and you also have beta, which are clotting hormones. Complement, and then you have your gamma, which is an antibody as well. Positive, negative. So you have hematocrit, which is the percentage of blood that is red blood cells. So that is red blood cells, and this can lead to an increase based on like gender, whether it be a male or female. Males have a higher hematocrit, females have a lower. And then at higher elevations in training, that can affect it. And they also lack a nucleus or a mitochondria, so they're an erythrocyte, and their shape is a biconcave. And this provides more surface area for oxygen and carbon dioxide exchange, which helps them kind of like band. So you can think of it as like this. So say that this is our red blood cell. Wow. Red blood cell, which is around 4 to 5 mil, around 40 to 50%. And then what it looks like is that they're basically just like these random like little squiggles, but in the middle right here, in the middle right here, you would have your heme, which is made up of iron, right? And then oxygen would be on the outside right here. That's what it would look like for an alpha, but for a beta, it would look more so kind of like this. It's just more like encapsulated here. the heme, and then you have the oxygen within this part. So fetal hemoglobin, it has to be gamma instead of beta because of the subunits that hold on to oxygen more tightly, and it can release it more easily, right? So we have hemoglobin, and hemoglobin is the only protein that transports oxygen that is minimally involved in carbon dioxide transport. Let's see what else is in this. Explain how heme is broken down. Okay, so let me talk about erythropoiesis real quick, which is the process of producing new red blood cells, and that occurs in the red bone marrow of the axillary skeleton. And red blood cells are only last the breaking down of red blood cells. So breaking down of red blood cells. This happens in the spleen for the most part, and then red blood cells, they are flexible and they can move easily, so they get old, which means that they get less flexible, which is why they get replenished so often. So in the spleen, cords of Billroth, it catches the flexible old red blood cells, and the macrophages engulf it. So we have our macrophage right here. Our macrophage, which then engulfs basically our red blood cell. And then you have your little heme right here, which is like, let's say it's kind of like two, and then, just something like this. Not trying to be an artist or anything, but yeah. Okay, so you have heme, which has iron in it, and these little positive guys right here. You have your nitrogen, which is important to its chemical component because it just is. So heme, it's not water soluble, so it can't dissolve, but it'll go across the barrier. So heme oxygenates, and then it becomes biliverdin. It's water soluble, and then biliverdin, it goes through biliverdin reductase, and then you get bilirubin, which is basically the twisting of the H bands, and with itself, it's not water soluble. Albumin binds to it though. Albumin binds to it. It's yellow. It's an antioxidant, and babies can have too much of it, which means that they'll get jaundice, which will mess with their ETCs in the brain, degrading, which would cause a degradation in their cells. So what happens is that they'll use a blue UV light, which will break the bond, the hydrogen bonds, and expose the polar parts to make it water soluble, which I think was actually really cool. But I don't know. Now we're in the liver. And it's becoming, so this is our bilirubin, and it has these little G groups on them, and it becomes this conjugated bilirubin. So bacteria eats the sugar, and then it becomes urobilinogen. This could be yellow, which is lipid soluble. And that could potentially go into the blood and become, so we have our urobilinogen, which could go to the kidney, urobilin, or we could get stercobilin, which is brown, and you have your intestine here, and then the colon. My iPad is gonna die soon, but that's okay. Yeah, so if we go over to right here. Okay. So this whole everything that's happening is happening in the spleen. So you'll have the breakdown of heme to bilirubin. So we're going from heme to bilirubin, which occurs in the macrophages of the spleen. So let's say we have our macrophage out here, engulfs the red blood cell, and then unconjugated bilirubin. Unconjugated bilirubin is transported to albumin through the liver. So we have our bilirubin here now in the liver. And then bilirubin is taken up by the liver and conjugated with glucuronic acid, which is what these G's are. They're surrounding it. And then it's gonna conjugated bilirubin is secreted into the bile and goes into the intestine. And then in the intestine, we have our glucuronic acid basically being removed by bacteria, which is resulting in bilirubin to be converted into urobilinogen. And urobilinogen is nonpolar. And some of the urobilinogen is going to either be reabsorbed and from the gut and enter the bloodstream again, or a portion of it is going to go into the enterohepatic urobilinogen cycle, which is going to be up here in the kidney. And then the remainder of the urobilinogen, it's not in the kidney, but it's either going to go out. And then we have the remainder of the urobilinogen being transported by the blood to the kidney. The kidney converts it to urobilinogen, which is urine, or urobilinogen remains in the intestine and is converted by bacteria to a brown pigmented called staurobilicin, which is and coagulation. And then we're giving special attention to platelets and coagulation cascade. Okay. So, hemostasis. Hemostasis. So, the thrombus, and then we have our embolus. Okay, so the thrombus is where we're going to have a clot anchored to the vessel wall where it formed, and then the thrombus breaks away from the vessel and circulates into the vascular system. So, whoops. Okay, cessation of bleeding is basically what an embolus is. And then our vascular spasm, which is basically a pain that causes a reflex to contract blood vessels to stop bleeding temporarily. And then we have our platelet plug, which is going to help us maintain homeostasis. So what's going on here is that when we do have an embolus, the platelet plug comes in handy. Wow, that is awful. Okay, so the platelet plug. So, right here, let's go ahead and draw this. And then right here, this is going to be our little, what is this? Not the basement membrane, but the epithelium within the vessel. And then up here on both ends, this is going to be our basement membrane. of the capillary. So what happens is we have von Willebrand factor, which is a protein that's secreted by the endothelial cells. So these are the endothelial cells. The endothelial cells that allow platelets to be activated when it binds to collagen, and then binding to exposed collagen in the vessel wall causes platelets to bind directly to collagen, but is not efficient during high shear conditions. So activated platelets bound to VWF cause an increase in calcium, which causes exocytosis of granules. So what we have here is like our little platelet, and we also have like these pores within the membrane, which I'm just going to go ahead and open right there. Yep, right there. Okay, so we have our platelets, we have our ADP receptors, granules, all of that. I was right, okay. Hello? Sorry. Okay, anyways. So we have VWF. Let's just draw that like this. VWF, which is basically going to bind to this platelet, which isn't activated currently, and it's secreted by the endothelial cells, and it allows for platelets to be activated when it binds to collagen. So when we activate these platelets, they're bound to VWF, which causes an increase in calcium, which then causes an exocytosis of the platelet granules. Someone's playing some music out there, and it's actually really annoying. What if I threw my drink on top of their car right now? Okay. Activated platelets, so what they're going to do is they're going to secrete alpha granules and dense granules. So let's do alpha granules, which then release chemicals that activate the additional platelets. So they're going to activate basically these platelets. And then these platelets from the dense granules are going to release ADP, and that's going to bind to these P2Y12 receptors on the surface of the platelets, which are going to cause an decrease in prostaglandin and calcium. And then thromboxane, which is a fatty acid from the membrane, is created by arachnoid. So we have thromboxane, which is going to be on this newly activated activated platelet. And then platelet aggregation is a process where platelets are rich in actin and myosin, so they're able to contract to form a compact platelet plug. And then you've got regulation, which is the endothelial cells blocking the platelet by reducing calcium levels in the platelet. So, you got these little guys in here, and then GP1B, F receptor, which is basically what's going to be up there. Yeah. I don't know what I'm going. Goodbye. All I've ever known. And you took me by surprise. Okay, so this is going to be our clotting cascade. So what we first have is a tissue cell, and this is tissue factor number 3. Man's careful daughter, the best thing that's ever been mine. Actually, hold on, I need to go over this. I just went over this in my head. Never turn back. Okay. So, tissue factor 3. What happens is the cascade goes from 12A to 11A to 10A. So we have 12, 11, and then it goes to 10, which then, this is activated all by collagen up here, being activated by collagen. And this one is going to be our extrinsic, well, this is going to be our intrinsic. So 11, which is our Hagman factor, is going to be turned into 12A because of this negative charge in the basement membrane, which is then going to convert 11 to 10 right here. This is our intrinsic pathway in the blood vessels. And then things that you could use to test the intrinsic pathway would be a drug called heparin, which activates antithrombin, which inhibits heparin is going to inhibit 12A, as then it's going to follow that cascade of, inhibiting 11A, and then 10A, and then 11. And then we have our extrinsic pathway over here, which is going to activate our 11A. But we start here. It's still going to end up in the same spot as here, but we're starting up here from the basement membrane as well. So we have 12A, which then is converted into 10A, activated by, so this one is activated by damage to tissue that releases thromboplastin. So this one we could think of like, let's see, let me get like a little, like, ow, there's something in my skin now. That's what it's activated by. And then it's going to release thromboplastin. Thromboplastin is this guy right here, which is also known as tissue factor. Tissue factor. Everything now, meet me in the pouring rain. Factor 3. And then that kind of basically ends it. But either way, these both end up kind of getting to the same end because you have cofactor here. Factor 2A is thrombin, which is right here. And then factor 1 is fibrogen, right here. Factor 1A is a dense fibrous weave to which blood congeals, and then it's fibrin, 1A. And then we're going to go through the common pathway, which is right here. Both of these end up going into the common pathway. So, factor X is going to join with factor V, calcium, and the platelet surface phospholipids form prothrombin activating complex. And then thrombin, which is factor 2, is going to turn into thrombin, and then fibrinogen is going to be activated via positive feedback, which, yeah. I don't know what I'm saying anymore. And then we need to talk about plasmin. Plasmin dissolves fibrin. And then this is activated by TPA. And then some tests that you can run to test a person, to test a person's plasmin is through a PTT test, which is prothrombin time, which is a blood test that measures the spread of clotting through the extrinsic, sorry. You can also do a PTT test. Sorry, this one is just PT. This one's our PTT. This one measures the blood clotting through the intrinsic. I was right. Okay. They're both blood tests. Sorry, I should definitely pause this. Okay, so blood clots form in conjugation with pre-existing platelet plug, meaning that upon the clot formation, we have clot retraction. And during clot retraction, we have actin and myosin contained within platelets of the platelet plug to contract. And then these proteins, when they do end up contracting, the web of platelets connected to the muscles by fibrogen begin to retract and condense, which is kind of like what we're trying to show up here at this point, is when they when they converge to each other and they stick to the epithelial layer, endothelial cells. Clot retraction decreases the cut of the gash by drawing in the damaged blood vessels towards one another, which will decrease the size of the cut. And then the fibroblasts and the epithelial cells will proliferate around the clot that serves to help repair the damaged vessel.